The purpose of my PhD thesis is to test the use of Arctic river discharge data as an indicator for permafrost thawing rate. Permafrost refers to soil that remains frozen for over 2 consecutive years. With climate warming, permafrost is thawing. This leads to many environmental hazards such as infrastructure subsidence, methane release, or river contamination with mercury. Permafrost underlies 20% of the planet and is mainly present in the Arctic, where its sustainability is crucial for ground stability, water resources, and local habitats. Thus, it is key to assess the rate of permafrost thawing process. This process occurring underground, it is not so easy to observe it directly. The permafrost lies under a soil layer called the active layer, which depth varies from centimeters to few meters. This superficial layer, sensitive to air temperature variations, freezes and thaws seasonally, while permafrost remains frozen. Through years, if winter is not long or cold enough to penetrate the active layer to its base, the permafrost table goes deeper. Thus, with increasing air temperature, the active layer thickens, leading to thinner permafrost. This is why the active layer thickness is often taken as an indicator to assess permafrost thawing rate. Currently, most of the active layer analyses are local in space and seasonal in time, while we aim at observing long-term active layer thickening process at the Arctic scale.
Do you have the appropriate data for such a study?
The Arctic is a freshly explored environment, and on-site data collection programs were rare before the 80s. However, in the 60s, many Arctic rivers were instrumented for water management purposes. As a consequence, river stream flow data is one of the rare Arctic data available with such a large time and spatial coverage.
But what is the correlation between Arctic river discharge and active layer thickening?
While thawing, permafrost releases water to the above active layer, which increases its groundwater contribution to the adjoining river. This contribution increase can be observed through river discharge evolution.
And how do you quantify this correlation?
We conceptualize the interaction between the river and the active layer through a simple model. The active layer is assumed to be an unconfined aquifer of thickness d, saturated with water and underlain by permafrost, which is assumed impermeable. The active layer reacts to a precipitation event by generating an horizontal outflow Q into the adjoining river. Both the river outflow Q and the active layer thickness D are related to the hydrologic parameter A by equations 1 and 2. This hydrologic parameter is called the recession constant.
And how do you obtain the recession constant of a catchment?
The method used is the analysis of the river discharge evolution through time. During recession, river discharge follows equation 1 and the rate of its decay provides the recession constant A. With statistical tests, we infer recession constant trend over a 30-year time period for each of the 336 studied catchments.
And what did you expect as a result?
As permafrost thaws, the active layer thickness D increases, and relying on our conceptual model and Boussinesq equations 2, the recession constant should increase together with active layer thickening.
Is that what you observed over your 336 catchments?
No, most of them, 65%, reflects a decreasing trend in recession constant A.
Why?
It could be that the conceptual model we relied on is not valid in cold regions. Indeed, The relationship between the active layer thickness and the recession constant might not be so direct, and other parameters than the aquifer properties could control the recession constant evolution.
And have you tried to verify this option?
Yes, we have tested the reliance of recession constant evolution on 10 different superficial, subsurficial, and climatic parameters that are known to have crucial impact on permafrost dynamics. Then we proceed to a multivariate analysis through a regression tree that tests correlations between each parameter and assesses their influence on the recession constant trend.
And are there correlations?
Yes, we identified parameters that favors the expected reaction of the catchments, that is increasing trend of the recession constant, and others that favors the unexpected opposite trend.
What did you infer from these correlations?
We were able to identify two scenarios. First scenario, where permafrost is maintained in extent by thin snow cover and thin vegetation cover. This high extent permafrost scenario limits the groundwater to the so-called supra-permafrost aquifer, and groundwater remains in the active layer. The second scenario, where the permafrost is reduced in extent due to a thick cover of snow and vegetation which warms the soil. This loss of permafrost extent creates intra-permafrost corridors where groundwater can travel from supra to sub-permafrost aquifers. The groundwater flow path gets more complex and diverse aquifers other than the active layer are connected.
The true complexity seems to deviate from the simplified conceptual model.
Indeed, our conceptual model assumes the aquifer to be unconfined and the groundwater flow to be horizontally directed towards the river. In scenario 1, where surface parameter and low topography limits ground flow to supra-permafrost, these assumptions are verified. However, in scenario 2, where permafrost extent gets lower, intra-permafrost connections are created, enabling vertical flows. The groundwater flow cannot be considered horizontal anymore. Besides, the phenomenon is intensified by high topography, which favors groundwater to reach deeper sub-permafrost aquifers that are confined by the above permafrost. The aquifer cannot be considered unconfined anymore. We can conclude that contrary to previous studies, a majority of catchments exhibit decreasing trends for recession constant A over the time period 1970 to 2000.
This initial result questioned the applicability of Boussinesq equation in cold regions.
We were able to identify factors that support direct relationship between recession constant trend and active layer thickness evolution as suggested by the conceptual model.
And factors that may complexify the relationship between recession constant trend and active layer evolution, thus invalidating the conceptual model.
This study is not the first that tries to improve the robustness and the adaptability of river discharge analysis method to cold regions, but it is the first one that analyzes so many catchments spread all over the Arctic.
Over a 30-year time period common to each catchment.
And with an extended range of potential controlling environmental parameters.
Finally, these results are great base for future modeling projects.
I would like to thank you, René Terrien and Sentinel North program, who supervised and funded this PhD project, and you for your attention.